again, from the graph that we obtained here, this is the trend. We have a switch on, switch off, and that time. Switch on and switch off, and so that time. This is a plotted graph on the diode. So on the average voltage that across inductor, see the S, 0. Switch on, switch off. So when we plus on and off, it becomes 0. So V out is equal to, we arrange the formula, become Vs D plus D1 divided by D1. And also on the average diode current. And so we can find from the average diode current is the area under the triangle shape here, equal to half of I max times D1. Half of I max times D1. So D1 here, half of it. So that's the amount of the area below the graph. So I max is the same as the change in inductor current when the switch is off. Is closed means switch is on. So this is the amount of I max. The delta I that happen inside our inductor is equal to Vs times dt over L. So this is our I max here. Okay, the maximum current in this continuous mode. So this is the maximum current that happen here on the DCM mode. So when we substitute ID into the equation, so ID here into the I max here, so we shall get the, so for D1, the duty ratio becomes of D1 V0 equal to V0 divided by Vs times 2L R dt here. Okay. Instead we follow the sequence, we shall get the D1 duty ratio formula of this value. Okay, we substitute the equation of D1 here into the equation of the V out. We shall get the amount of output voltage in relation to input voltage V out divided by Vs. How much the gain of the output compared to input. So it's equal to half of this formula. Okay, means that the boost converter will be much highly depends on the combination of the RLF and the amount of our load, inductor value, and also the frequency that applied to the system or to the topology, and also including the duty ratio of the operation in the CCM or DCM, and duty ratio. That's what we can see. Duty ratio we cannot exceed, let's say 70 or 80% to reach the ideal operation of what we expect. If we increase more than that, so the amount of resistance that happen or contribute by the inductor component will affect the output voltage or magnification or the amplification. Okay, to conclude, the boost converter can step up the output voltage without a transformer, but we have certain limitation on that. And due to single transistor, we have only one switch, so it should have a high efficiency conversion system, no? And the input current is continuous. However, at a high peak, the current has to flow through the power transistor. A high peak current has to flow to the power transistor. We have single transistor only, so we should be aware or alert on the high peak current. The output voltage is very sensitive to changes in duty cycle. It might be difficult to stabilize the regulator. As what we can see just now, we have a situation whereby from unity to maybe 2 times or 3 times or 4 times, the curve much linear in terms of linear form, but when reached from 0.6 to 0.9 duty cycle, the trend will be, the changes will be much steeper, so we cannot stabilize. It's not ideal to stabilize the output on the range, on such range. Okay, the output average current is less than average inductor current by factor of 1 minus D. And much higher RMS current would flow through the filter capacitor, resulting in the use of higher or larger filter capacitor and larger inductor than those on buck regulator. Compared to buck regulator, the boost might have to use higher value of filter capacitor and also inductor capacitor filter and also inductor filter. Higher value means higher cost, so we should consider that in our design. Okay, next we go directly to the last chapter of our DC-DC buck DC-DC converter, which is on the DC buck boost converter. We talk about buck converter, which is to step down, boost converter to step up, and now buck boost, which the capability of the converter which can step up or step down our input based on the control of our duty cycle. So this converter are capable of stepping up or stepping down. So this is the special or the preference of the buck boost. Okay, the components in terms of component wise, the element is almost the same. We have switch, inductor, capacitor and diode. But in terms of arrangement, we can see that the arrangement of the diode is on the reverse bias. The placement of the inductor here. So we shall analyze in terms of their output graph consequently. But we have to take care or take note on the assumption that we made here. Okay, the output voltage can be either higher or lower compared to the input. We have to assume for this converter it happened in steady state analysis, means that it already switched on a few cycles, reach stability, and with other assumption is that such that the inductor current is always continuous on the CCM mode, continuous current mode. Average inductor current is 0, average capacitor voltage is 0, and all other components are assumed as ideal. So assumption made if you refer to the books. So converter operates in steady state, inductor current continuous, and the amount of up and down is 0. Capacitor is large enough, the capacitor here is large enough to maintain the constant output voltage, and the switch is closed for the duty cycle times total period, and close mean on, open mean off, on and off for another 1 minus cycle times the tempo or the period. And all other components are ideal. The inductors are ideal, the voltage drop is not considered here, and the ESR is not considered as contributing factors of losses. So that's the initial assumption that made on the buck boost converter for this part of time. Okay, next we go on the topology that and on the output waveform from the topology that we have to analyze what are the pattern and the output from the circuit. If we take a look on the inductor point of view, on the output point of view, on the capacitor point of view, okay, the voltage and current waveforms we have here from the inductor point of view in terms of their current, in terms of their voltage on the inductor point of view, their inductor current, inductor voltage, and also we have here capacitor current, and this is what output diode. Okay, the output, the diode current. Okay, diode current. Okay, we have here inductor current, inductor voltage, diode current, and also capacitor current. Okay, this is the on state during on or during the switch is closed. on, and during the switch is open or off. So for me, I prefer to use on and off. So on means that the switch is closed, the switch is closed, switch on, the switch is off, disconnected. Okay, we have diode here. Okay, we analyze one by one, during on state and during off state, from inductor point of view. When we switch on, so the inductor will have the full power or voltage comes from the source. So all the source deliver the current to the inductor. You cannot go to the diode because this is reverse bias, or reverse bias, you cannot go in, so it considered as open. So the total current will flow through the inductor. So we have here the flow from positive to positive of inductor. So when we take a look on the inductor, we can see that it will ramp up from minimum to maximum value. So this is the plot during, we have assumed that it happened during stable state or steady state. By right, if we plot from the initial state, we will start from 0, ramp up like that. Okay, but now we are taking at steady state, means that from maybe the period that already steady. So means that it happened on the minimum and raise up to the maximum here. Maximum during where the duty cycle is switch off. Okay, when we on, it rise up. When we switch off, there will still current that flows or contain or store inside the inductor. We will try to keep flows. When we switch off, so switch off. When we switch off means that disconnected. Now the diode here will forward bias. Means that the current will flow. It's no more going here, but it go to another branch of the capacitor, to the load, back to the inductor. So means that it still will disperse the remaining current inside the capacitor down to the another branch. So means that it will flow down, and it will flow down from maximum I that contains inside our inductor now, down to the minimum state of the current. So we consider that the inductor is ideal. It does not emit or absorb any current. So it starts from certain level, rise up, and we go down to the same level as the previous level it has. Okay, so when so it complete one period, another period start, it will ramp up again, and it will go down again, so it will repeat itself. Okay, so this is from the current inductor current point of view. So from the inductor voltage point of view, okay, so this is the voltage. So when we apply voltage, so we have here V VL. We have here VL. Sorry, this one is the current that supply to the system. Is the source current. Sorry. So the source current, same. It starts with the minimum current that flows into the system, and it raises up to the maximum. So IL mean maximum, also the same here, but during a switch off, the current will stop supplying, so we maintain it at 0 until the another cycle start. So it start from minimum up to maximum and turn to 0. And from our source point of view, in terms of this is the inductor point of view in terms of their voltage. So we have a positive voltage during first on cycle here. So the total of source voltage applied to the inductor. So we have positive VL applied. Then when the switch is off, so switch is off, the voltage that applied or applied from the inductor is the amount that applied to the